So when we want to talk about chirality, what we're really talking about are mirror images. So just a mirror image, this is our line here, this is a mirror, everything has a mirror image. Me, these stick people, just funny shapes, even molecules. Everything has a mirror image, of course, except vampires, mirrors and garlic being effective against them. But let's come back to that. Let's talk about isomers. We know that we have our structural isomers, which are also known as constitutional isomers. Constitutional. And these have the same molecular formula, but different attachments of the atoms. So we can take a look at this. Here we have just regular pentane, C5H12. That's pentane. But we can move one of these methyls. Let's put it right there. Same molecular formula, C5H12, but now we're dealing with 2-methylbutane. These are two constitutional isomers. But we also have something called stereoisomers. So stereoisomers also have the same formula. It's a similarity across all isomers, same formula. Stereoisomers also have the same attachments of the atoms. So what's different? How are these different at all? Well, they differ in the 3D arrangement of the atoms in space. That is to say, their configuration is different. Let's look at some examples. So we can draw a molecule and its mirror image. Right here, here's pentane, looks pretty much the same. Let's look at something else with a functional group right here. Let's add some 3D arrangements to this. So we have 2-butanol here and its mirror image. Notice on the left, the hydroxyl is on the left, and on the right, it's on the right, because we're looking in a mirror. They look pretty similar. But we can look at this, we can flip this over. Let's put this hydroxyl on the left. Let's go ahead and flip this molecule over. So now we have our hydroxyls on the same side, but notice now the hydroxyl is facing away from us. And these are two different molecules. These are two stereoisomers. So even though they look very similar, these are in fact two different isomers. And this is an example of the difference in configuration. So let's take a look at these. Can we take these molecules and can we put one on top of each other? Are they superimposable? Because if we can superimpose two of these molecules, that means they're actually the same thing. So we can flip this over like we did. We can rotate it again. Let's rotate it. Now our hydroxyl's down here, and our hydrogen's here. We can do pretty much anything we want to it, and it's not going to be the same molecule. There's no way we can get that hydroxyl and that hydrogen in that same configuration as we had to start. So they're not superimposable. So a molecule that is not superimposable on its mirror image is called chiral. That's chiral. Let's look at some other examples. So we can draw this right here. Okay, so we have 2-propanol. Let's draw it again. Okay, there's our mirror image. But here we can see these are in fact superimposable. We can take this one on the right, this 2-propanol, and just remind you real fast that the dark solid line means it's towards the viewer, coming out of the screen, coming out at you like these hydroxyl groups, and the dashed line means we're going away. So we can look at these, and they are in fact identical. We can take one of these 2-propanols and move it on top of the other one, and they're exactly the same. So a molecule that's superimposable on its mirror image is achiral. So how can we tell if it's chiral or not? Well, there's one simple thing we can do. We can look at the molecule and see if there's a plane of symmetry running through this molecule. So we flip it around, look for it, see if we can draw a line where half of the molecule is the same as the other half. So looking at 2-propanol, we can see if we just turn this molecule a little bit, we can draw this plane of symmetry right here. That might be hard to see, so we can draw this from a different view. Now we're looking straight on. That going straight down is our 2 methyl groups, and one behind it, there's our hydroxyl and our hydrogen. Right there, boom. Plane of symmetry, therefore it is achiral. But let's go ahead and take a look at our 2-butanol right here. And we can draw this view right here. Right here we have our ethyl group and the methyl group in the back. And there's the hydroxyl group and our hydrogen. But because those two functional groups that are on the bottom are different, there's no way to find a plane of symmetry. So 2-butanol is chiral. We can look right here at this carbon. This sp3 right here has 4 different attachments to it. Let's draw this out right here, just a planar structure, methyl, ethyl, hydroxyl, hydrogen. 4 different attachments on this sp3. And this is a chiral molecule. And in fact, this carbon is known as a stereogenic center. And it's usually carbon, doesn't have to be, but it's usually an sp3 carbon when we're talking about a stereogenic center. And finding these stereogenic centers typically means you're going to have a chiral molecule. Not always, but we can find our stereogenic centers right here in 2-butanol. We know that's chiral. We did the mirror image, we know it's chiral. It's not superimposable on its mirror image. But what if we add another functional group to it? Okay, now we have 2,3-dihydroxybutanol. There are 2 centers here. Let's take a look at this. Okay, just drawing it right up here. Let's take this mirror image. Going down on the inside. This one's coming out. Okay. Notice right here we have a sigma bond. And remember what we can do with sigma bonds. This freely rotates right here around this bond. So we can do that. We can just turn one of these around. What do we end up with? We end up with this molecule right here, with both of our hydroxyls coming straight out the page at us. And we'll turn this one too. And we end up with the same thing. Just after I just turned it around, just rotated it a little bit, and there we see, those are the same molecule. That is in fact achiral. So, as a rule, a compound with a single, just one single stereogenic center, it will always be chiral. Always be chiral. One center, always chiral. But with more than one stereogenic center, 2 or more, it is sometimes chiral. That requires a little bit more work. And that's chirality.